Welcome to another edition of Math for No Reason. In this edition, we are going to discuss about the Flett's mean value theorem. We all know about the Rolle's theorem, which states that if f is a real valued function which is continuous on the closed interval ab and is differentiable on the open interval ab, and fa is equal to fb, then there exists a point c in between a and b, that is a less than c less than b, such that f prime c is equal to 0. Based on the Rolle's theorem, one can deduce this very famous result due to Lagrange, known as the Lagrange's mean value theorem. Here we have the same hypothesis as that of the Rolle's theorem, that is, this real valued function f is continuous on the closed interval ab and is differentiable on the open interval ab. Then the Lagrange's mean value theorem asserts that there exists a point c in the open interval ab, that is a less than c less than b, such that f prime c is equal to fb minus fa divided by b minus a. You may note that the right hand side is the slope of the secant joining the points a comma fa with b comma fb, and the left hand side is the slope of the curve at the point c. So it essentially says that in between a and b there is a point c where the slope of the tangent at that point would be same as the slope of the secant joining the points a comma fa with b comma fb. That is, your tangent is parallel to the secant. Now, Flett's mean value theorem generalizes the Lagrange's mean value theorem in a very interesting way. And this result was proved by Flett in the year 1958. So it is in that sense a recent result. It says that if f is differentiable on the closed interval ab, and it happens that f prime a is equal to f prime b, then there would be a point eta in the open interval ab, that is a less than eta less than b, such that f prime eta is equal to f eta minus fa divided by eta minus a. Note that in the Rolle's theorem we had this condition fa is equal to fb. In Flett's theorem we have the condition f prime a is equal to f prime b. Now the result that we get, f prime eta is equal to f eta minus fa divided by eta minus a, essentially tells us that the tangent to the curve y is equal to fx at the point eta passes through the point afa. So here is a geometric illustration of that. We are looking at this cubic function x cube minus 3 by 2 x square plus half x, whose derivative is 3x square minus 3x plus half, and if you put x is equal to 0, you get f prime at 0 as half. If you put x equal to 1 in the derivative, you would get again half. So we see that the f prime 0 is equal to f prime 1. That is, the slope of the tangent at the point 0 is equal to the slope of the tangent to the curve at the point 1. So the tangents to the curve at the point 0 and 1 are parallel to one another, as can be seen here in this figure. Then the Flett's theorem asserts that there will be a point eta in between 0 and 1. At that point, the tangent would pass through the point 0, 0 in this case. Okay. So 0, f0 in general. And the red line here gives us that. And one can work out that the Flett point in this case, that is the point eta, is 0.75. Now, to prove this beautiful result, we have to go through steps. And the first step is to define this auxiliary function g on the closed interval ab to r, given by fx minus fa divided by x minus a, if x belongs to the half open interval open at a, closed at b, and is equal to f prime a at the point x is equal to a. From this definition, we see that the right hand derivative at a is equal to f prime a, and therefore g is continuous on the closed interval ab. So this is an important point to note, that g is continuous on the closed interval ab. For x belonging to open a, closed b, this interval, this half open interval, the function gx is equal to fx minus fa divided by x minus a can be differentiated simply by using the quotient rule, which gives us g prime x is equal to x minus a f prime x minus fx minus fa whole divided by x minus a whole square. So this is a result that we will need to remember. We begin by assuming f prime a is equal to f prime b equal to 0. We will relax this condition later, but for the time being we begin with this, and it immediately gives us that g of a is equal to 0. If gb equal to 0, we will have ga equal to gb, and g is continuous on the closed interval ab, and g is differentiable on the open interval ab, as we have seen. Therefore, Rolle's theorem is applicable. And by the Rolle's theorem, we would get a point eta between a and b, where the derivative of g would be equal to 0. Now, g prime eta equal to 0 would mean that here the numerator is 0. Rewriting that, we would get f prime eta is equal to f eta minus fa divided by eta minus a, which is the claim of the Flett's theorem. So if gb equal to 0, we have proved the claim. Now the question is, what if gb is not 0? Suppose gb is greater than 0. G prime b, expression that we see here, would reduce to minus gb divided by b minus a, and since gb is greater than 0, this quantity is less than 0. So g prime b is less than 0 and gb is greater than 0. Now g prime b less than 0 means g is decreasing to the left of b. That means there has to exist a point x1 lying between a and b such that the value of g at the point x1 is greater than the value of g at the point b. Thus we have 0, which is equal to ga, is less than gb because gb is greater than 0, and that is less than gx1. Now since g is continuous on this interval a to x1, by the intermediate value theorem, there must exist x2 between this interval a and x1 that is a less than x2 less than x1, such that gx2 is equal to gb. Now the moment we get that, we see that the conditions of the Rolle's theorem would now be applicable on the function g over the interval closed x2 to b. And hence, we will get eta, where eta lies between x1 and b, such that g prime eta equal to 0, and we have seen that g prime eta equal to 0 yields the Flett's mean value theorem, and we are done. GB is less than 0, we can argue in a very similar manner, and we will again get g prime eta equal to 0 for some eta lying between a and b. Now remains the last condition, that is, we had assumed that f prime a equal to f prime b equal to 0. What if they are not equal to 0? F prime a equal to f prime b, but the value is not equal to 0. Then we will consider a new function hx, which is defined as fx minus x f prime a. Then h is differentiable on this closed interval ab, and you can easily check that h prime a equal to h prime b equal to 0. So we are back to the condition under which we have proved the Flett's mean value theorem already. So we can claim that there is an eta between a and b such that h prime eta is equal to h eta minus ha divided by eta minus a. So this is the conclusion of the Flett's mean value theorem applied to the function h. Now if you do some straightforward algebra, from here you will be able to show that f prime eta is equal to f eta minus fa divided by eta minus a. So again we get the Flett's mean value theorem. Therefore, we have proved this theorem. If f is differentiable on the closed interval ab and f prime a is equal to f prime b, then there exists a point eta, a less than b, such that f prime eta is equal to f eta minus fa divided by eta minus a. This concludes this edition of Math for No Reason. Thank you.